anything embarrassing. But for this particular webinar, we've set a record both for the number of people registered and currently the number of people online attending the webinar. So I'm really excited about this. This is kind of fun. Really makes me feel good. This is the kind of feedback that I like to get from this, that we're doing something that people find interesting and worthwhile, and people are willing to give some time to have a listen to what we've got to say. So go over the rules again. Please do not use the chat window to interact with me. I will not be monitoring it. Anytime during the broadcast, during the webinar, you may use the questions input. I most likely will not respond to it during the webinar. However, I do go to it at the end when we open it up for questions, and I will try to get to the questions as they are asked in the order in which they're asked. So if you've got any questions, feel free to throw them in there at any time during the webinar, and I will get to them at the end. I think that is all the housekeeping that we've got. So and then it looks like our attendees number has started to slow down as far as people logging in. So I think we've got most everybody who's going to be joining us today. There may be a few stragglers, but that's okay. Luckily, being virtual, nobody's going to open the door and disturb the class while we're talking. So with all that being said, let's go ahead and get started with what everybody apparently wants to hear about. Today's webinar is when BOD goes wrong. And this is something that anybody who's worked in the wet chemistry portion of a wastewater lab, a commercial environmental lab, any of those types of areas, this is something that you get chills when people say it. Your BOD QC failed, your blank's too high, your GGA's off, and all of a sudden you get this feeling of dread. And so I think that's what everybody wants to know. Now, I am not expecting that after this you will always and forever have perfect BOD results. That is not my promise. That is not my intention. That is always our hope, but unfortunately life gets in the way. So what I'm hoping to get out of this really realistically is that we'll get some tools to be able to identify what happens when our BOD presents problems, when our BOD is not well behaved, to be able to get it better and get it back on the right track. So just a real quick refresher, probably everybody knows these things. However, sometimes I find it helpful to review really the basics of what we're talking about, just so we can all start from the same background, same level, so we know what we're talking about. BOD, biochemical oxygen demand. This is not a chemical test, despite the word chemical being in the name. Biochemical is what we're working with. That means that there is not, it's not going to be a chemistry type of reaction that happens. You don't get to use Beer's law for spectrophotometers. You don't get to have a linear ratio of if you've got this much, then you're going to have this much. We expect that it's approximately linear with things, how things work, but it's not always going to be. And that's because we're working with microbes. We're working with living organisms. My favorite thing to say is that although the microbes know how to multiply and divide, they're not really good at math. Pause for laughter. Everybody go ahead and chuckle, yay. So BOD, it is a method-defined analyte. BOD is the result of what is in your sample and how the microbes interact with it. It's not a physical particle. There is no BOD molecule. BOD is an effect on the water, on the oxygen in your sample. The microbes eat things that are microbe-sized or smaller and that are tasty to them. And in the process of eating, they live, they grow, they die, they reproduce, they respiration, the respiration process. So all of that is happening, and in the process of doing all of that, the microbes are consuming oxygen. So what we're measuring is the amount of oxygen consumed by your microbes as they are doing microbe things. So it's, like I said, BOD is not a particle. It's something that is happening because of what is in the sample. So those are all the reasons why the test itself doesn't always behave like we want it to, and why there can be problems. Other reasons that contribute to the problems are the timing issue. Holding time for BOD. If we say holding times, and everybody's going to say 48 hours, or some of you may say 24 hours, depending on how you read standard methods and how it's being interpreted, but generally 48 hours is the official holding time listed in 40 CFR in that preservation and holding time and so forth table. Standard methods ask, if you can do it within 24 hours, but you do have that full 48 hours. So 48 hours from the time the sample is collected until the time the sample must be in the incubator with its testing going on. But unfortunately, we have a 5-day incubation duration, which means that by the time the test is done and you get all of your results and you find out if you did it right, you cannot go back and redo those samples. The samples are now out of hold. Now, why is that holding time there? Remember, because you're working with microbes, because you are working with the depletion of oxygen as the microbes are consuming the microbe food, the bacteria food in your sample, if it's held for too long, then you have then the microbes are already consuming what is available in the sample, and you will not get a proper representation of what would happen from its natural state. Theoretically, freezing that sample could entirely halt any degradation, but the method specifies, or I guess 40 CFR specifies, that these samples are not to be frozen, and I believe it is because that would potentially compromise the integrity of the various molecules of what are feeding the bacteria. So you may mess up the ease with which the bacteria can digest that food particle, or even potentially interfere with the bacteria themselves. So you've got a strict 48 hours that you cannot alter, and then your test takes 5 days. So all of your timing is a problem with this, and we've all experienced it. We all know what it's like. When your sampler brings in that last minute BOD 2 minutes before you're supposed to go home, but it's going out of hold before you get in the morning, so you've got to stay and set those up. And even better if it happens to be at a time when you really wish you didn't have to take it off 5 days later. So all those things that we have to look at with BOD. Let's talk first about what's never going to happen, our perfect situation. I say never because, and that's not true. It happens a lot. Overall, most of you, most of the time, are getting good results. We're looking at, and I actually left a bullet point off of this, I just realized. We're looking at our blank depletions, we're looking at our seed control bottles, we're looking at our GGA results, and we're looking at the individual sample depletion. So all of those things need to fit certain guidelines in order for you to be happy with how your BODs ended up. Unfortunately, we don't always get the perfect situation, and we get scared. That's the scariest font I could find on our default PowerPoint. So that's the scary font we get at the top, and then we have our scary bacteria here. This is the most interesting slide I've got in the whole thing. The rest of it is a lot of text and charts. So get your fill of eye candy here, and the rest of it you'll just have to read and listen to me talk. All sorts of terrible things could happen. We could have our blanks fail. We could have our standards fail. I didn't put the seed on here, but that's our seed failing there. It's getting angry and scaring us. We could have bad dilutions. Lots of things could go wrong in our BOD batch. So let's start with our QC. And we're going to start with our blanks. The method requirement, depletion of not greater than 0.20 milligrams per liter. I pulled this out of the 22nd edition, I believe, of standard methods. Remember, with standard methods, it is the year of the revision that is important for the approved versions. I believe the 21st and 22nd editions both contain the appropriate method. I don't remember if the 20th does or not. Pay attention to the significant digits in this requirement. In the 22nd edition, it says not greater than 0.20. I believe a previous version that may still be valid actually says 0.2. The new version, the 23rd edition, which has a later revision date, specifically says a 0.2 depletion, not 0.20, and it actually says average, using the average of your blanks that you've set up. So why is that important? What does that really mean? Most of our DO meters measure out to the 100th of a milligram of oxygen, and so what that means is if you're using a 0.2 requirement, then if it depletes 0.21, that actually rounds to 0.2 and is valid. If you're using a 0.20 requirement, then 0.21 does not count. It is not valid, and so that would be a failure. Pay attention to the method that you're citing. Pay attention to the actual requirements. That may give you some leeway in what you're working with. But in any case, 0.2 of some sort is our target. And most of the time we can hit that. Occasionally, however, we do have a greater than a 0.220 depletion. There's nothing you can do once that happens to fix your results. Some people would want to say what sounds reasonable of, well, if it's more than 0.2, then I can just subtract the excess from all the depletions in all my samples. It sounds like a good idea, and it's got a reasonable basis behind it, a reasonable, I mean, the math somewhat works out. However, unfortunately, there's some real complications in that because you don't know if it is a straight value because of potentially an error in your DO meter. Maybe it's slightly off in its calibration, and so it's just a total, it's a complete shift of 0.5 or excuse me, 0.05 too far, or if it is a proportional in amount to the amount of dilution water that you have. So there could be something in your dilution water itself that is contributing, in which case you would have to find the amount, the proportion of the dilution water that you put in each sample and correct for each individual fraction of that amount. And so there are lots of complications. So the method specifically says you may not correct for excess and blank depletion. What could be some causes of your blank depletion? We talked about one, your DO meter could be off. This was more of a problem back a few years ago before the luminescent probes became more common. Generally speaking, the luminescent probes are not as prone to calibration errors as the old, I forget what they're called, galvanic, I think. Those electrochemical probes that had the membranes on top. They were very dependent on the weather conditions in the area. If you had a front move in while you were doing your DO reading, that could potentially throw things off. If you had significant barometric pressure differences between setting up and taking off, that could definitely affect how you read things. So you had to be very careful with those older probes that they were calibrated correctly so that you had an accurate reading. The newer luminescent probes are not as big a problem. So if you're using one of those, most likely your probe is correct. You can do some, each manufacturer has some different ways of checking them. So check your user manual for that probe in order to figure out how to do a saturated and a zero oxygen check. But your source water itself could also be a source of the issue. lots of people use different sources of water for what they are working with. Remember, your source water is the water that you start with. Once you add all of your nutrients and everything to it, it becomes dilution water. So your source water could be a source of your problems. A lot of people will use water out of their DI tap, and that can be good, but you have to pay attention to how your DI water is being generated. If it's truly deionized water, then it has run through some kind of ion beds, and those resins are some form of organic material. I don't know exactly what those deionizer resins are, but they can cause problems. I know the system that we had in the lab where I worked, we always knew, even if they didn't tell us, when the tanks got changed, because we had some serious issues getting our source water stable and usable. Before sometimes it would take a day to flush through the pipes to get to our BOD water room before we got good water coming out of there, and we really had to struggle with it. Also, those resin beds are prime places for bacteria to form and to incubate. And so if you do not have some kind of sterilization procedure in your deionized water process, then your source water actually could contribute bacteria into your test before you even get started. And that will lead to excess depletion, because that'll be bacteria that you are not accounting for. Those of you who may aerate your water while you have added your nutrients in, the point of adding the nutrients is to make that source water into water that is good for bacteria to live in, which means that whatever you've put in there for your aeration is going to build up bacteria food, essentially. You've now made that a good place. And so just in the course of using, a lot of people will use the aeration stones or some kind of bubble dispersion apparatus to get your water up into a fully a saturated source. And that can also introduce bacteria into your water as you're preparing it. So if you're using some kind of aeration in preparing your water, you want to make sure to clean that regularly. Some kind of hypochlorite, bleach, chlorine of some sort will do wonders in keeping that clean and making sure you don't have any kind of scum or bacteria buildup that you're introducing into your water. Also, be very careful if you're using a pump that you want to make sure you use an oilless pump. Any pumps that generate pressure, if it's an oil using pump, then it can aerosolize some of that oil and discharge it through the air produced by the pump. So you want to make sure that you are not doing that and adding that into it, because that will be a definite cause of problems with your blank water. If you're using glass bottles that you're having to reuse, those can become contaminated. Everybody knows about the problems with cleaning them. They require some effort. So you need to make sure that if you're doing reusable bottles, that you have a vigorous cleaning protocol. Again, sterilization of some sort using some kind of bleach or chlorine compound is highly recommended. I know a lot of people will then also use an acid wash afterwards to help to remove any other organic buildup. Nitric acid works well in removing organic deposits. Hydrochloric acid can also work well, but that usually has a problem with chlorine gas generation, so you just have to be careful with that. Sulfuric acid also can work well. It's not quite as good at removing the organic deposits, but it can work. So whatever protocol you have, make sure that you are using it and don't kind of gloss over those steps in your maintenance and your cleanup afterwards. Also, my last note down there, beware your nitrification inhibitors. If you do CBOD and you're adding that nitrification inhibitor, do not add it to your blank. The nitrification inhibitors in and of themselves can cause oxygen depletion. And it will usually show up in the 0.2 to 0.5 range. So it's right there. The minimum amount usually is just enough to make your blanks fail, even if you have nothing else that is contributing to it. Now, it is normal that you get 0.05 or so, 0.07 that happens, even if you truly have a sterile solution where nothing has happened and there's no actual physical reason for the oxygen to deplete out. Very rarely can you achieve optimal conditions where the bottle remains saturated. So you will have some slight oxygen depletion just in the course of, because that's just how life works. So that less than 0.1 depletion is perfectly fine if you're consistently there. You're in great shape. Even if you're consistently at 0.15, that's fine if it really does just stay there. BOD is a good test to make sure you use control charts because they can help you identify trends. Rarely does a BOD all of a sudden just fail out of the blue. If you have one that just fails all of a sudden out of the blue, then that's usually a one-off. It's not often a systemic problem, and most likely your future test will be back to your normal practices. But when you start seeing trends going one way or another, that's when you need to start paying attention and start trying to find problems before they're truly a problem. All right, let's move on to our seed control, our second set of QC. So is there an actual requirement for the seed control values? Back in when I first started learning BOD, that 0.6 to 1 milligram per liter was gospel. We were not allowed to exceed that in either direction. And that came from, I believe, the 19th edition. I have a typo, special bonus cool points if you find any typos in my presentation. But the current edition of standard methods, DO uptake attributable to seed generally should, those are the important words, be between 0.6 and 1. That is in 5210B 5D. And so that's the section where it tells you how to add seed and kind of what you're looking for. Generally and should are not absolute requirements. The absolute requirement is in section 7B. Seed control samples, yep, there's another typo, do not meet the above criteria in all dilutions. So this is, samples should be qualified if seed controlled samples do not meet the above criteria in all dilutions. So what it asks you to do is you set up multiple bottles of your seed in order to calculate the oxygen depletion due to the seed so that you can use the math to correct for that in your final results. The criteria that it talks about are a minimum of the minimum depletion of 2.0 milligrams per liter and a 1.0 milligram per liter oxygen minimum residual. That's the 2-to-1 rule that I like to refer to. So if all of your seed control bottles do not meet that requirement, that is when your seed has failed. The new version, which we hope will be included in the next method update rule, actually only requires one bottle to pass. And you just do your math off that one bottle. But that is the actual requirement for your seed control to work. Now, once again, I forgot to mention this at the beginning. I am not an auditor. I am not a regulatory body. I am not the EPA. I have no authority to say this is the way things are. I only speak the way I interpret things and how I feel like they should be. And unfortunately, the David Smith common sense rule does not always apply in all situations. So be sure to consult with your auditors, your regulators, the people who write your permits, and make sure you follow their guidelines. If you would like to discuss with them and present well thought out and reasoned arguments why you think it should be a different way, drop me a line. I'll be happy to back you up and share what insight I have. In some cases, I can even talk to people for you. But they do get to have the final say. Reasons why your seed might fail. Age of the seed, and this could be either age sitting on your shelf or age for how long it's been in solution since you made it. Most commercial seeds, they give you instructions to rehydrate the seed, and then they give you a 6-hour window that you can use it. I never knew whether that 6-hour window started from when you first put the seed flakes into the water to start rehydrating, or if it started after you allowed it to stir and you've got your seed suspension. I never knew when that 6 hours really was, so I always told everybody, I think it might have been 3 hours or 4 hours is what we kind of used just to make sure we were safe. But your seed can age as it's sitting on the counter. You don't have a lot of food in that dilution water that you use to rehydrate, and if you don't keep it well aerated, then those bacteria can just start to collapse. That bacterial colony can collapse on itself. If you are using your own seed, if you're lucky enough to be in a wastewater plant or someplace where you've got a consistent source of seed, that is truly the best seed to use for your sample, just because you're going to be using bacteria that are acclimated to your waste stream. And that's a great thing to do. But again, maintaining that seed source, if you have a tank or something in your lab that you're trying to maintain, that can also be a possible variation in your seed results. That, and if anything ever happens to upset your plant, not that any of you ever get an upset plant, but if the other guy's plant ever gets upset, you'll know that that can definitely affect the viability of the seed that he may be able to use. And so you can commiserate, maybe loaning some of your wastewater or something to use, or maybe just shake your head and say, gosh, I'm glad that's not me. Because we always know that it never happens to us, it's always the other guy. But usually the seed is an easier thing, again, because there's less of a strict number that you have to work with. The seed is usually less of a problem. Even if it creeps up to 1.1, 1.2 or so, that's not terribly outside the range. And if you're able to use the criteria of the minimum depletions and minimum residuals, then that's not even an issue at all. The seed is typically something that we consider in our next potential failure, our GGA. This is probably the most common one that I get questions about, that people will call me asking what's going on. So our GGA, the glucose glutamic acid, that is our standard for BOD. And the 300 milligrams glucose and glutamic acid concentration that we use, 6 milliliters of that dosed into 1 BOD bottle, the BOD value that you achieve from that should be 198 plus or minus 30.5. And there's a nice explanation in some versions of standard methods about where that came from, but that's just basically years of data statistically averaged, and that's a couple of standard deviations away from the average that they achieved. Interestingly enough, and I did have someone ask if I could address this in the discussion, that 198 plus or minus 30.5 is the value. There is no BOD value and separate CBOD value. Standard methods is pretty clear in that they expect the same result for both variations of the test. Now, if you're like me, you wonder how that could be, because CBOD deliberately inhibits nitrification, and the glutamic acid has a nitrogen functional group on it. There's nitrogen present in there, and how you can inhibit nitrification and still get the same result, I don't know. But we've all seen it. When we do our CBOD analysis, our results generally are lower. Now, usually they're not low enough that it falls outside that 1 67.5 for your low value, but sometimes it can be. And that's always tough to figure out what to do. Standard Methods has a reference that I can't remember the exact thing. I couldn't find it when I was scanning through the method to pull the exact quote out. But basically their instruction is to add more seed to your standard if your CBODs come out too low. And somehow adding more seed will then help to increase that GGA value. It seems counterintuitive because you feel like the subtraction, the correction that you get for adding more seed, you would just have more correction that you take into account, and so you would end up with a net zero in your math. But it doesn't actually work like that. As you add more bacteria, you do have a higher consumption of the source food material. The seed control or the seed correction factor that you are taking into account is just the depletion from the just from bacteria, not from the bacteria acting on the sample. So, and this is actually, if we're going to skip over the middle bullet point, go to the bottom bullet point. If your GGA ends up with low results, that is usually the fix to help get things back on track, is you need to adjust your seed concentration. This can be harder because you don't have, it's tough to figure out exactly the best way to do it. I'm going to use polyseed as an example, not because I think everybody should use them, but just because that's what most people are familiar with. Their instructions say to take 1 capsule of that polyseed and rehydrate it in 500 milliliters of your dilution water. And then people add different amounts of seed. I think we used 3 or 4, depending on how things were. I've talked to people using as high as 7, 8, or 9 milliliters of seed. I don't know that I've had anybody really going lower than 3, but the amount of seed that you add in can be important, as is the concentration of the seed in your suspension when you're doing your dilution water. So instead of using 500 milliliters of dilution water, possibly only use 400 or 350. I think we've gone down as low as 300 sometimes with some of the batches that of polyseed that we used. If you have the option, try a different seed source. There are other seed sources available. Talk to the local wastewater treatment plant, see if they've got something they can help you out with. There's at least one other commercial supplier of dehydrated seed that you can give a try. So try out a few different types of seed and see if you find one that consistently works. I don't know why some work for some people and some work for others, but it's true. I've seen it happen. It's happened to me before. We had issues with one brand of seed and switched over to another one, and it worked. And then there were other people who were using that exact same brand that we and same lots that we had the first time, and they were getting fine results. So I don't know why, but changing seed sources can be helpful. But if you have low results for your GGA, try working with the amount of seed that you are adding, either by adding more of what you're currently doing or by using less dilution water, thereby ending up with more bacteria per milliliter of seed that you add. Either one of those can help out. With high results, that is usually a result of either overdosing the bacteria, the seed in your bottle, or some other one-off error. It often will be accompanied by high blank results, and so the two of those usually go hand in hand, and if you can fix one, then you'll be able to fix the other. Again, all of these fixes, all of these things that we work with are not always difficult, might not be the easiest word, but tiresome, time-consuming to fix, because when you're doing any kind of troubleshooting, in order to actually identify the problem, you only alter one thing at a time. And in order to alter one thing and to see if you fixed it, it takes 5 days. And in that time, you're still working with other samples that you're hoping are passing as well. And so just to try 3 different things can take you 2 weeks if you are managed to get them set up back to back to back. And so that troubleshooting of BOD can be a problem. All right. So let's move on from our QC to our sample. Our sample actually does have potential to fail. We run sample duplicates, and we have our depletion requirements. So again, the same as we were talking about with our seed earlier, our samples have a minimum depletion of 2.0 and a minimum residual of 1.0 milligram per liter. And then our replicate samples need to be within 30% difference. So these are all failures. If your failure is that your minimum depletion of 2.0 is not met, that can be a non-issue if your bottle that you've used was 100% sample. If you used all sample and it did not deplete enough, then you've got a non-detect. That's easy. You report it as 0. Even if you do have some dilution that you have done on that bottle, you can report a less than something. And as long as that is less than your permit limit, that is perfectly fine. You've got no issues with that result. It becomes a problem if your less than is higher than your permit limit. The other end is if your minimum residual of 1.0 milligram per liter is not met, that's a big problem, because that means your BOD value is greater than what you have set up to achieve. And so that's when you really don't know what kind of results you're looking at, and cause all sorts of problems. The minimum, if you do not meet the minimum residual of 1.0, that is a mandatory reporting qualification. If you don't meet the minimum depletion of 2.0, that may or may not require qualification of your data. And avoiding that is all about being familiar with your sample and being able to choose good dilutions. And we're going to look at that on the next slide. Talk real quick about replicate samples outside the 30% difference. All that ever really affects is that one individual sample, and it just requires qualification of that sample, that there is some kind of matrix effect going on with that sample where it is not a consistent value. There can be some other sample oddities that occur. I have seen where the DO value actually increases from a sample over time. That has always been attributable to peroxide being present in the sample. Some of the older versions of standard methods do not address testing for peroxide in your sample pretreatment. The newer methods, newer versions do put that in there, and so they ask you, and there's just peroxide test strips that you use, quick dip in and look for color change. One thing that they don't tell you how to do is how to treat it effectively. I think the recommendation is to just stir it well and let it sit in the sun with the presumption that UV rays will decompose peroxide. That's great if you've got time and access to the sun, which many labs don't, time or access to the sun. I never had a window in any lab room that I worked in, so and setting a sample outside on the patio is not a great idea. That's really uncontrolled, and who knows what could happen. But stirring it, vigorously shaking, that can help to degrade that peroxide. Some other issues that I've seen are if you've actually got a case of sample toxicity, and that will show up in a really weird depletion pattern for your samples. If you've got multiple dilutions set up, it's hard to see with 2, 3, 4 bottles, but if you do more than that, you can usually see it better. And it's where normally the oxygen depletion will be a somewhat linear relationship with the amount of sample, but if the oxygen depletion kind of tapers off and plateaus with the more sample you've got, that is usually indicative of a toxicity effect. And basically what's happening is the sample itself is killing the bacteria and not allowing them to do what they're supposed to do. How to choose good dilutions. One thing that always helps, or that I have found very helpful, is the COD estimation technique. Now, I am not talking about looking at the official COD value of the sample, because that can sometimes be considerably higher than the BOD of the sample. And this is something that I developed just kind of as an accident in the lab where I worked, and it gave us some pretty good approximations. What we would do is we would take our COD vials, and for best results, you'll want to use the mercury-free vials, because then that's less of a hazardous disposal concern afterwards. And you add 2 mL of your sample to the COD vial, shake it up, and just let it sit for about 15 minutes, long enough to cool down. It gets really hot when you add that sample in, just because of the reaction with all the acid in there. And so that heat of reaction, that exothermic reaction that you've got going on, is enough to approximate the BOD value. So once you've let it cool down enough so that you can hold it, put it in your spectrophotometer and calculate it against a regular digested COD curve, and it will do a pretty good job of giving you an idea of the BOD value of your sample. If you've got historical results for a sample, and you need to come up with a dilution scheme, I use these numbers. So if you look on the left side of this chart, those are sample volumes. I don't like using percents, just because doing percents of 300 milliliters is not easy in my head, whereas these numbers in sample volume are pretty simple, because our common laboratory dispensers measure in those values. You know, we've got 1 ml and 2 ml and 5 ml pipettes. We've got 100 milliliter graduated cylinders. You know, easy stuff to work with. So the idea here, and let me grab my drawing tool. There it is. I think we'll use the highlighter. I've never used the highlighter before. Let's see what happens. So what you would do, the idea behind this is you kind of get an idea of the range that your sample has gone in. And let's say you're working with a sample that has a high value of, let's say, 1,000 historically, and a low value of 500 historically. So my intent with this is that you find kind of the edges of what you want to do. So here, we're going to look for 1,000 under the 8 milligram depletion. So 2160 is kind of the edge, although 1080 might be something also that we look at. So, but that's really close to it, so we want to make sure that we encompass. So let's start here. So 2160, and then with 500 being the bottom, so honestly this same range, 360, but just to give ourselves room, we're going to go all the way down. We're going to use this 400 as our range. So what this is going to do is, if we use dilutions of 1, 2, and 5 milliliters, then if with a saturated bottle, we start with about 9. So if it depletes 8 at 1 milliliter, then we'll be able to read 2,160 milligrams per liter of BOD, which is plenty. So we expect probably it will only deplete maybe 5 or 6. But then if we get the bottom end of it, if it really is only about 500, we will get at least 2 depletion. We'll be able to get down to 360. So 3 depletion is 660. So somewhere in this 2 to 3 range at the 1 milliliter amount will give us the right number. And then we've got a really safe value right here in the middle of the 2 milliliter range that will give us a good number. And if for some reason we've gone way lower than normal, our 5 milliliter amount will still give us something up here in this range that will give us a good readable number. So what we're looking at, what we want to do with this chart is try to find the edges of what we expect on the sample and use those to encompass the dilution values that we're working with. All right, so I've done a lot of talking now, and that's the end of my prepared presentation. So what I want to do now is open it up to questions, and let's see if any questions have started coming up. All right. Here we go. Let's swing the question panel out. Yes, thanks. That's the word I was looking for. We can see a presentation. Okay, people. All right. First question: why does the final DO take a long time to show up when doing the GGA and the polyseed? What's the relationship of COD and BOD? All right. Why the DO takes a long time? So that's actually a good point. Going back to the original discussion of BOD, there's some really interesting graphs of how the depletion works. And with our 5-day BOD, we actually are not getting a full, complete depletion oxidation of everything available in the sample. That is just a good amount of time to compromise between maximum depletion and minimum time spent. Usually, honestly, for the GGA, you've got pretty good mathematical relationships at about 2 days, maybe 2.5 to 3 days, where you can still get a valid number that will give you a good, consistent result every time. The problem is that not all samples follow that pattern, and some samples, some actual real-world samples, take your full 5 days in order to be consistent in the results that they produce. So that's why we are using the 5-day. If you've ever read any of my other stuff, my Understanding BOD Lab Matters online, you'll see my somewhat humorous hypothesis involving Shakespeare and the witches from Macbeth. I like that idea. It's just as viable as any other explanation that I've seen. But the 5-day is merely a compromise between time and completion. There are some countries that do 7-day BODs. I think I've seen some places where a 3 or 4-day BOD is acceptable. So that's just kind of how that works. And can you calculate, so how do you calculate results for a BOD result a day or a week late? You can't. That is an invalid test, at least for regulatory purposes. If you do your own development of things and you have non-regulatory things that you want to do, you can develop a BOD calculation for longer periods, but those are not reportable for BOD. If DI systems can contribute significant amounts of bacteria, what would you suggest for source water? Good question. I meant to mention that. I know a lot of people will actually purchase what is called steam distilled water, and you can get those at the grocery store. You'll have to look at the label to see how that water was prepared, but if it says steam distilled on any of your distilled waters, those will be good sources. You have to be careful that it does say steam distilled. There are other distillation methods. Usually they use copper stills, and that can leach, obviously, copper ions into the water. Copper is antimicrobial and will cause some severe problems. So purchasing water just from a grocery store can be a good source. That's not as viable for anybody using copious amounts. I know we would have days where we would go through maybe 100 liters of water in a day. So that would get kind of pricey if you're a big lab doing that. But again, if you've got the budget, that may be worth your time. So that is something to investigate. Should the seed be constantly aerated while we use it, or just up until we start using it? That depends on whether you are planning on using it again afterwards. So again, speaking from my experience, where we had multiple batches that we would prepare in succession to one another, we would aerate the seed to stir everything up, and then We'd let it settle for 10 or 15 minutes for the flakes to settle out and decant all the liquid off the top. We had a nice cloudy bacteria solution. We kept that bacteria solution constantly aerated, even when we were using it. We had, I hope this bottle is still in use there at the lab. I don't know if it is, but we had a specially designed Erlenmeyer flask with a large opening on a side arm, essentially, kind of at an angle, where we could, we had a screw top on top of the Erlenmeyer, so we could screw a bottle top dispenser on, and then we could put an aeration pump stone down in the sidearm flask opening. And so we could aerate the seed suspension while we were dispensing it. And that's kind of what, that's how we worked on that. Discuss the toxicity effect. We did talk about that a little bit. As far as I know, reporting toxicity is simply identifying it as toxicity suspected. Usually you will have to, a good practice would be to include the depletion results for the wide range of dilutions that you did, showing that the depletion amount tails off and plateaus at a certain amount. The fix for high GGA failure, it's identifying the source of excess depletion in your blank water. That is typically the result, or how you end up with a high GGA failure. We currently do not use nitrification inhibitor in our CBOD QC. We use the same QC for BOD as CBOD. Is this an issue? Do we need to change this? I think so. From my understanding, you should add the nitrification inhibitor to your GGA bottles, so that you are showing how it's interacting with the standard. If your auditor is okay with what you're doing, then keep on doing it. If your auditor doesn't know what you're doing, then you may want to address that before it gets noticed. I would recommend starting to add that nitrification inhibitor to your GGA bottles. Maybe just do a separate set initially until you see what happens, so that you know kind of how to work with it and how to adjust for it until you have to start reporting it. And then, but do try to get that in control so that you know what's going on, so that you can start using it. That is something that you should be doing. Since the minimum depletion is 2.0, does this mean a value of 2.02 or equivalent would be rounded to 2.0, or does 2.02 fail? That's a really good question. I don't know that I've ever taken that into consideration. I guess I've only ever used rounding rules when they're in my favor. Kind of like Monopoly, bank error in your favor, collect $200. Rounding rules in your favor, let it go. Rounding rules not in your favor, don't round. But let me think. Since we are trying to go more than 2.0, and I'll have to admit I did not pay attention to if that 2.0 is a 2.0 or if it is 2. So check your method to make sure of the significant digits reported there. But I guess if it is reported as 2.0, then it would be something that you would need to take into account with your rounding rules. Remember, just be consistent with your rounding rules and how they are applied. How do you differentiate toxicity from a matrix effect? That's a good question. I don't know. That probably would require a lot of study and a lot of familiarity with your sample. Matrix effect will typically only show up in significantly different results in a duplicate. Toxicity you would see over a wide range of dilutions that you have done on just one replicate. They could manifest themselves in similar ways with similar types of results, but it is a hard thing to really distinguish. I think I've only ever encountered 2 toxicity effects in all the samples that I ever did in the 7-8 years or whatever that I was doing BOD. So yeah, that's something that you will have to investigate on a per sample basis. Our lab read somewhere, probably in the same method, yes. that if the sample is extremely strong, needing to use less than 3 mils per bottle, we need to dilute the sample. Yes, that is correct. Standard methods, the more recent editions do have instructions on that light. Basically, you'll just need to do a decimal dilution, so a 1 to 10, or if it's really, really strong, a 1 to 100 or something, and then dispense the appropriate amount adjusted for that dilution into your bottle so that you can add the correct amount. So let's say if you're adding 0.5, 1, and 2 mils of sample, and you did a 1 to 10 dilution or a 1 to 9, 1 plus 9 dilution of that sample, then you would add 5, 10, and 20 milliliters of that diluted sample. And the reason to do this is so that you get a homogeneous, well-distributed sample so that you can be consistent with how much you're adding. It's tough to add homogeneous amount less than 3 mils. So the COD estimation technique, is it true that the COD result will be about 2 to 3 times higher than the BOD result? Sort of. So if you do a full COD on a typical wastewater stream, that's a pretty good number to use. Using the COD estimation technique, my experience has usually been it's closer to maybe 1.5 or sometimes equal. So it'll be a lot closer when doing that COD estimation technique. And remember that that is not heating at 150 degrees for any amount of time. That is simply adding the sample to the vial, let the heat of reaction and mixing do some reaction for you, and then measure it once it's cool enough to handle. All right, Bianca, I am going to, that's a good long question. That's going to probably be just an individual phone call. I'll look your email up in the registration list and see if I can get in touch with you and see if we can discuss that. Next question, what's the best way to strip excess DO? So the best way to do anything as far as DO, whether to bring it up or to bring it down, is simply to shake it. If you have excess DO, that means your sample is super saturated, so agitating your water will remove the excess DO. If your sample is undersaturated, so down in the 6 range or lower, 7, 6, 7 or lower than that, then you shake it and you shake extra oxygen, mix oxygen in, and that will bring your DO value up. If you're really high, if the water is very cold and it's up to like 10 or 11, it is possible to bubble nitrogen through it, but you have to be really careful with that because there's no good way to tell how long it'll take to displace the oxygen and get things back in line. I've tried it before and severely undershot and ended up with a DO of like 3 or something. I had to go the other way around. And with that, we are essentially out of time. There's a lot of questions left. I am going to see if I can, I'm going to save a copy of these questions, and I'm going to try to put some answers up. I'll include a link to that. We will have a link of this. The webinar will be posted. We'll have it up on our website, maybe Friday, possibly Monday, depending on how busy our website guy is. But you will all receive an email with a link to where that will be. Thank you, everybody, for coming. Appreciate your attendance. We had a lot of people here today, and I'm excited about that. I'll get more of these questions answered and get those out to you as best I can. Thanks, everybody. Look for emails for the future webinars, and y'all have a great day. Bye.